Hello, everyone. My name is Ainemba Asbita, and I'm going to talk about the two models that we trained for our project. So one of the models is transfer learning audio classification model, and the second one is transfer-based poetry audio model. And both of these models, they follow different approaches to learn the patterns from the audio data, but aim to achieve the objective of detecting the respiratory disease sounds. So I'm going to first talk about a transfer learning audio classification model. In this model, the raw poetry audio recordings are first resampled to a standard sampling rate of 16 kilohertz to ensure consistency across all recordings. Then after that pre-processing, a pre-trained model, that is YAM-net, is used as a feature extractor, and it already has been trained on a large audio data set and is capable of identifying the meaningful sound patterns. Then after that step, that model processes the audio signals and generates 1024 dimensional embedding vectors, which represent important acoustic features of the sound. Then those embeddings are then passed into a fully connected neural network classifier, which learns to distinguish between healthy sounds and healthy, and then the background noise. Then finally, the model uses a softmax output to produce probabilities for the three classes, allowing the system to classify each audio accordingly. Then after, I'm going to talk about the transfer-based poetry audio model. For it also uses the same approach in the beginning, but the audio recordings are first converted into Mel spectrograms, which visually represent how sound frequencies change over time. Then these spectrograms are then resized into 2024 by 2024 pixels, allowing them to be treated as an image-like inputs for the model to learn from. Then a vision transformer is then used as a feature encoder, unlike in traditional CNN. Transformers use a mechanism that is called self-attention, which allows the models to capture relationships between different parts of the spectrum. Then this helps the model to learn complex sound patterns associated with the respiratory disease in the poultry. Then finally, the final output of the model predicts the health status of the chicken sounds and the severity of the respiratory conditions. Then after talking about their architecture, we're going to explain how these models learned. I'm going to first talk about transfer learning audio model. For it, the dataset used was 4,336 labeled chicken audio recordings, which was then divided into three classes, that is healthy, unhealthy, and then the noise. Then to evaluate the model effectively, the dataset was divided into a training and a validation sets using 80 out of 20 trained validation plate, of which the 80% was used for training and the 20 was used for validation. Then while the training, the model used a batch of size of 32 samples, and the training process was conducted for 50 epochs to allow the network to learn important acoustic features. Then the model was optimized using the Adam optimization algorithm, which automatically adjusts the learning rate to improve the training efficiency and convergence. Then after that training, the transfer learning model achieved an overall classification accuracy of approximately 79%. Then now I'm going to explain how the transfer audio model learned. For it used the same data set, and then it also has the same classes. The data was also split into 80% for training and then 20% for validation. And this ensures that the balanced presentation of each class during the model is evaluated. Then the model performance. Then to improve the model's ability to generalize for real farm environments, the data augmentation techniques were applied. That is the random noise addition and the amplitude scaling. Then also, transfer-based audio model for it was optimized with the Adam W optimizer, which incorporates weight decay regulation to improve training stability and reduce overfitting. Then the training also involved 15 epochs, and that model obtained the approximate accuracy of 81%. I'm now going to the next slide, which is about explainable AI techniques that are used to audit the models. After building those learning models, these are the AI techniques that are used to audit the models. The first technique used is SHARP, which helps identify the importance of different features in influencing the model's prediction. Then the next one is LIME. For that one, it helps explain individual predictions by showing which parts of the input contributed most to the model's decision. Then the next one is salience maps, and that one helps to visualize which parts of the spectrogram for the model focuses on when detecting respiratory sounds. Then finally, we use PCA, that is principal component analysis, that helps to visualize the learned embeddings and observe how different sound classes cluster in feature spaces. Then all these techniques, they combine together and improve the transparency, trust, and interpretability of the machine learning system. Then afterwards, I looked at the evaluation of these two models and the performance. It was generally evaluated by these matrices. One is accuracy, then next one is precision, then recall, and F1 score. The accuracy, it measures the overall correctness of the model's prediction. Then precision evaluates how many predicted positive cases are actually correct. Then the recall, it measures the model's ability to detect all the actual disease cases. Then lastly is F1 score, that provides a balanced measure between precision and recall. And based on this evaluation, a transfer-based model achieved slightly higher performance of 80% compared to 79% accuracy that was achieved using the transfer learning classification model. Yeah, basically, those are the two models that I managed to train for our data. And yeah, thank you for listening.